everything. Okay, yeah. So today's a quiz day. It's gonna go like the other quiz days, and that I'm gonna spend. There's like one more problem I wanted to go over from the notes of this week. So again, I'm in like the notes I handed out this Monday. So there's one problem I want to go through on the notes, and then there's a problem on the quiz I wanted to go through from last week that people had difficulty with. And then there'll be a practice quiz for like 15 minutes, and then the actual quiz for 15 minutes. As time goes on, it's going to be harder for me to write practice quiz problems that are like similar to the quiz problems without being the same. So um, I don't know. Like I try to make it so that practice quiz helps with the quiz, but sometimes it's going to be less of a help than others. Okay, yeah. So what I wanted to talk about, at least for maybe like 10 minutes today, are these generalized unions and intersections. This isn't really anything mind blowing. So let's make sure I'm actually recording first. I am. Okay. Yeah, so this is kind of just taking the idea of unions and intersections that we did last Wednesday, or I should just say on Wednesday, and then just making it so instead of just having a union between two sets, what if we had a union between n sets, or like an arbitrary number of sets? So the union of a collection of sets is a set that contains those elements that are members of at least one set in the collection. So we denote this union as the following. So if we have n sets A1 up until AN, you can take the union of all n sets and it will look something like this. Right? This is really just a collection of sets that are in A1 or A2 all the way up to AN. If it's in one of these sets, it's going to be in the union. And then conversely, we have the idea of the intersection of a collection of sets. This is the set that contains those elements that are members of all of the sets in the collection. So similarly, you just flip the cup into a cap, or like the union into an intersection. So an element X is only going to be in this intersection if it's in A1 and A2 and A3 all the way up until A. Right. So it has to be in every set in order to be in the intersection of all the sets. So it's the same idea as we were doing before, except now we're just adding more sets into the mix. And on the homework, you'll have more practice. I'll ask you to draw Venn diagrams where you're representing these intersections and unions, and you'll have like 3 sets to consider. So you'll have some practice with the homework. There's just one problem I wanted to go through. Oh, I should make this remark as well. I'm not sure if this is really going to show up too often in this class. Maybe it will, maybe it won't. But you don't need to stop at a finite intersection or a finite union. If you change the n to infinity, you can take the union or intersection of infinitely many sets. So you can index these sets by like the integers or like the natural numbers or something like that. So you can have an infinite union or an infinite intersection. So I just wanted to go through one example here, and then I wanted to go through a quiz problem from last week. So for this example, we're going to suppose A1 is equal to the set of numbers up until I. So it's like 1, 2, 3 up until I. And so for this problem, it wants you to find the infinite union of this set. So it wants you to find this infinite union from I is equal to 1 of AI. So we want to determine what this set is going to be. And then it also wants you to find the intersection of this set as well. Or of these sets, I should say. This set right here. And I know I kind of just introduced the concept, but I'm going to throw it out to the class anyways. So if I wanted to find the infinite union of the A1s, does anyone know what this would include? Like what would it look like? Does anyone know?
When it comes to unions and intersections, I'm thinking unions will include every number in every set, which will therefore be all real numbers, and the other intersection will just be whatever numbers are in every set, and which I believe would just be 1.
Yeah. So I'll get to the intersection later. But yeah, for A1, it's not going to be all of the real numbers in that we're not including like the numbers between 1 and 2. But I think I understand what you're saying in that as long as like we have an element in one of these sets, it's going to show up in the union. So if we were to look at like A1 is just the set 1. A2 is the set 1, 2. And then if you keep on going, we have that A1 or AN is equal to 1, 2, all the way up until N. And so we're not stopping where our N is. Like N can go from like 100, and then we can do like A 1,000, A 1,000,000, A 1,000,000,000. So you just keep on going and going and going. It never stops. So we know like 1 is in the set, 2 is in the set, everything up until N is in the set, and N never stops. So this is really just the collection of, I guess, like whole numbers from 1 onwards. So it'd be like 1, 2, 3 onwards. So you can rewrite this as being the natural numbers without 0. Let me try and draw that a little bit better. So you can draw this as the natural numbers without 0, which is also the same thing as doing the positive integers. Right, so that will be the union. Let me create some separation between kind of like the aside I just had and the answer. And then the intersection, that was correct. Like the intersection, you want to look at the elements that are in every single set. And if you look at A1, A1 only has 1. So the intersection can have 1. But then like 2's not in A1, so 2's not in the set. 3's not in A1. The only number in A1 is 1. And it turns out like 1 is the only element that all sets share in common. So the intersection is just going to be 1. Right, this is the only element. So we have 1 is the only element in each AI. Right, and you can kind of give an idea just by writing out these sets. You'll see, I mean, they only have 1 in common. Okay, so that's generalized intersections and unions. And I guess I put in one part where I'm like asking, how does the infinite intersection differ from the finite intersection in this example? Does anyone see, is there a difference between the two? Do they differ at all? Yeah, I'm seeing people shake their heads. It's kind of maybe a trick question. Maybe I should have worded it better. Yeah, so it turns out like this intersection doesn't really differ at all from the finite intersection. If you did a finite intersection, it's still just going to be 1 for the exact same logic we were just looking at. Okay, any questions about this example? Okay, yeah, and so there's 2 other problems you can look at for additional practice. When I send the solutions out for the lecture notes later today, I'll make sure to include these in case you want to check your work. But this is really just the same kind of idea or ideas we've been looking at already through these. So before doing the practice quiz, there's one problem from quiz 2 I wanted to go over. So I'll pass out quiz 2 when you're working on the practice quiz. I think problem 1 generally went well. So for problem 1, it was asking like for all x, do we have like x greater than 0 or like x is less than 0? This is going to be false because if we let x be equal to 0, like it's not greater than 0 or less than 0. So this stands as a counter example. Problem 2 ended up being the problem where most people had difficulty, which wasn't really my intention. Like usually I try and make the problems like escalate in difficulty as they go on. So I tried to have like the negation one be the most difficult. But problem 2 was tricky for people. So for problem 2, it wanted you to find a counter example, if possible, to the following statement, where it was asking for all x and for all y, if x squared is equal to y squared, then x is equal to y. This is going to be false. For instance, if you had x is equal to -1 and y is equal to 1, if you take the square of these 2 numbers, they're both equal to 1. But clearly x is not equal to 1, which is not equal to -1. Oh, wait, I flipped it. This should be -1, and then this should be 1, which is equal to y. So a lot of people mess this one up. But you just need to find one counter example. I mean, there's like infinitely many. You can do like -2 and 2, so on and so forth. And then problem 3 was just applying, I think most people got this one. So it's just applying the negation until eventually they're next to the propositions. So like you flip the quantifiers, you flip the and then you turn this into a for all, and then you get this.
Sorry, it just the and the xy, the parentheses bracket that ends it looks a bit larger. So for a bit, I thought it was the but and not with the X and Y, but rather with the current initial parentheses for the entire thing, you know?
Is there an issue or like what do you? Yeah, is there like a problem with what I have written? I guess is my question.
I just thought initially, thought that when I first saw it, I initially thought that this was not compared with this, but instead this was compared with this because of their size.
No, yeah, I mean I'm not always gonna be that careful with like the size of the parentheses. I'm gonna admit that now. But yeah, I think it was problem two. That was where most people had the difficulty. But I mean, you're kind of new to this. By the first exam, um, you'll be masters. Okay, you'll understand how to do this, and there won't be a problem. Yeah. So the first exam, it's in 2 weeks. I'll do an exam review. Like I'll send out an exam review on Wednesday of next week. At this point, you've covered pretty much everything that's going to be on the first exam. It's going to be chapter 1 and chapter 2. So when I send out the exam review on Wednesday of next week, I'll send out an email. And then the week maybe like Wednesday before the exam, I'll post the solutions to the exam review. So you'll have a better idea of what I'm going to ask and I guess like what the difficulty of the problems are probably going to look like. And you'll have more practice.
Is Wednesday of next week the day next week that we're not going to be here?
Yeah, like I'm posting on Canvas and then I'll send an email out to everyone. So there'll be like an exam review page on Canvas that I'll make. Okay, yeah, so the rest of the class is just going to be dedicated to, I guess, practicing for the quiz and then actually doing the quiz. Let me stop recording. And then when you're